Okay, so flux. Remember electric flux. In general, the most general definition of flux is the double integral of E dotted with the vector dA. It's the amount of electric field that flows perpendicularly through a surface, and we add all that up. So it has units of E times area. This is in newtons per coulomb. That's E times meters squared. So for a very simple situation, if I've got just some area here, some flat area that's not changing, that's supposed to be a flat rectangle, and some electric field pointing through at some angle, then the dot product of two vectors is the product of their magnitudes times the cosine of the angle between them. So if E is constant and A is constant, flux is magnitude of E, area, A, times the cosine. My pen is not cooperating today. Cosine of the angle between E and the normal vector. You're going to have homework problems on flux. You're going to have test questions on flux. Like half the time, they're going to give you this angle here. That's the wrong angle. Here's my normal vector that points perpendicular to the surface. This is pointing straight up. I want this angle. So that's the cosine of this angle, not this one. Okay, if E's already pointing, if I've got some constant electric field pointing straight through some surface. So remember, flux measures how much of your electric field flows perpendicularly through a surface. If you're already flowing perpendicularly through, then our angle is 0, cosine of 0 is 1. So we would just get the magnitude of the field times the area. If we have an enclosed surface, so those were all like open little tiny rectangles. What if I have some 3D, maybe a sphere? So, oh my God, my 3D drawing skills are terrible. Imagine this is a sphere. Then the total flux through the entire surface, the total flux through over the entire surface. Sometimes we'll write this. You'll see me go back and forth. Instead of writing dA, I'll write ds. Those mean the same thing. Sometimes we get lazy in these two-dimensional integrals and we just write a single integral, when this really is a surface integral. If you were to actually calculate the integral, you would be doing a dx and a dy. So this really is a double integral, but sometimes we get lazy and only write a single. Sometimes we'll put a little s here to say integrate over the entire surface. This is a very, very hard Calc 3 problem. Very hard. However, the very last thing you learn in Calc 3 is there's a shortcut. You can use the divergence theorem. This is equal to the triple integral of the divergence of E dV. Now, I've already gone through this in another video. I don't need to rederive it. But this here, del dot E, that's Maxwell's first equation. That's your charge density. If I integrate over all the charge, this whole thing over here, it's just how much charge lives inside the surface. So this is Gauss's law. The flux through a surface is equal to, if this is a closed orientable surface, the total charge that lives inside that boundary divided by epsilon naught. So it turns out, instead of doing a really, really hard surface integrals are a nightmare. Gauss's law says you don't have to do it. There's an easy shortcut. So if I've got some charge here of 1 billion, I need another zero, 1 billion coulombs. And I want to know what the flux through this surface is. This guy's creating a gigantic electric field. He's got electric field lines that are flowing out of him, and they're going to be huge. All of these lines are going to be flowing through here. But whatever flows in to my surface is also going to flow back out. Think of the electric field like literally like currents. All of electrostatics was, even electrodynamics, everything we do from here on out was developed, and they were thinking in terms of fluid dynamics. And even though it's not a perfect analogy because nothing's really flowing, the math works out perfectly. Think of an electric field as currents in water. So whatever flows into my sphere here will also flow back out. So the total flux, the double integral of E dot ds, will be the charge that lives, oh, there's no charge inside, 0. Because everything that flows in, which we call negative flux, also flows out. We call that positive flux. Flowing out is positive, in is negative. What if I had a single charge in there? Let's say this is 3 coulombs. Then the total flux through the entire surface, this guy has electric field. The electric field points away from positive charges. It doesn't matter where the charge lives in there. It could live right up by the boundary. It could be right in the middle. It doesn't matter at all. The total flux through the entire surface is going to be that charge that lives inside over epsilon naught. So 3 over, and look, you would look that up. Epsilon naught is a number. You would think by this point I would have epsilon naught memorized, but I don't. You would just look it up, divide, and the answer is in Newton meters squared per coulomb. If I had, here, this is going to be one of your homework questions. If I've got this cube here, and I've got, say, an electric field, a constant electric field that's pointing to the side. So it's flowing across all of these 6 sides. These 2 sides over here and this side, it's passing perpendicularly through. It's going directly through those surfaces. On those 2 sides, the flux here would be E times A. Because the angle was 0. We're flowing perpendicularly through, and cosine of 0 is 1. Now this guy here, I'm flowing into the box, so this would be negative flux. All that stuff that flowed in here is also going to flow back out on this side. So over on this side, the flux will be the same thing, but positive. So the total flux is 0. What about this side up here, the top? What I'll try to draw this again. Again, my 3D drawings are not great. E is flowing along that surface. So we're not passing perpendicularly through the surface at all. E is parallel to that surface. It's just riding along the top of it. So the angle, remember, when I say this, this angle right here is the angle between E and the normal vector. So my normal vector, perpendicular to the surface, points up, E points over, they form a right angle. Cosine of 90 is 0. There's no flux here. The flux through the top, the bottom, the front, up here, the back, all of those are 0. What if we had, there's another homework question that's similar to that. So we've got a cube and we've just got one single charge sitting inside the cube. The question asks, how much flux passes through, I don't know, this side over here? Now, if you wanted to do this in a Calc 3 class, it is an incredibly difficult problem. You have to parameterize this entire surface. You got to find the electric field that this guy is creating and find the X and Y components of that electric field at every point along this surface. You have to do this really, like, it might take me a week to figure out the problem. And I teach Calc 3. It is a very hard problem. But Gauss's law says, no, it doesn't have to be. The total flux through the entire cube is Q over epsilon naught. Each side then gets 1/6 of that. So the flux through this side would be that over 6. We're done. So Gauss's law is very powerful. Okay, there are like 4, I don't want to call them challenging problems because they really are my favorite problems all semester, but 4 problems I definitely want you to be able to do. And I think I'm just going to go through all of them right now. Every one of them. I'm going to do them in all their glorious detail. So the sphere. So I think at least 3 of these I've already done before. I guess if you're watching this, let me make sure I don't need to make any more announcements. I don't think so. So if you don't want to watch me go through all the Gauss's law problems, feel free to stop the video here. I'm not going to force you to sit through problems you've already watched me do. I just kind of wanted to put them all in one place and they're here if you want them. If you're here live and you don't have any questions, then you don't have to sit through this. I've already done most of these for you. Okay, good. Everybody wants to stay. All right, so we have a sphere of charge Q. That's the total charge on the sphere. It's distributed evenly throughout the sphere. Radius is R, capital R. I want to find the electric field inside and outside. So inside would be at some radius less than R, outside some radius greater than R. Okay, let's do inside first. R less than R. So first thing I'm going to do is draw a picture. If you don't include a picture, you're not drawing a complete solution. My total radius all the way out is R. I want to go from the center to some little r. So I'm drawing this little sphere inside my big sphere. That's my Gaussian surface. So a sphere of radius r that's inside, smaller than big R. Okay, now just by the physical symmetry of the situation, I've got a whole bunch of charge Q spread out in here. And they're all positives. Q is a positive number. Electric field has to be symmetric. It has to be radially symmetric. Imagine, this is not part of the problem. I just want you to imagine if I've got some sphere here and this thing creates, even though it's all perfectly symmetric, it creates an electric field that points this way. Well, if I rotate, if you take your computer right now or your phone or whatever and rotate it 90 degrees, this picture is going to look identical. The sphere looks identical, but these arrows would be changing. That doesn't make any sense. It doesn't make any sense physically for a perfect sphere to not have spherical symmetry. There's no way the electric field points to the right. Because for you, it would point to the right, but somebody standing back here would say, no, it points to my left. That doesn't make any sense. You're both looking at the same spherical picture. We have to have the same kind of symmetry as the charge. The only symmetry that exists is pointing radially out. This is the only thing everybody's reference frame would agree on. So E must point out. So I've got my here's my big circle. Here's my little circle, little r. E points directly out from it. So on that surface there, so on that little sphere of radius r, E is perpendicular to the normal vector. That's important. Okay, so the double integral of E dot dA must be, by Gauss's law, the total charge that lives inside that little sphere divided by epsilon naught. That's Gauss's law. I just made the argument that E is perpendicular to A, to the normal vector. I need to also make an argument, wait a minute, what if E was bigger right here than it was right here? So I said it always points perpendicular. Could it possibly be different along that boundary? No. By symmetry, it wouldn't make any sense physically. If E was bigger on the bottom than the top, because if I rotate the ball around, now the top and bottom switch places. It doesn't make any sense. So E must be constant at that radius r. Okay, so that means this left-hand side, the dot product of perpendicular vectors is just the product of the magnitudes. So I went from dot there to just magnitude because of this. Because E is a constant, constants can get pulled out of integrals. Wait a minute, this over here, the double integral of dA, that literally means surface area. So this here is the surface area of a sphere, radius little r. We know that, or you should. That's 4 pi little r, that's my radius squared. Okay, that was the left side of Gauss's law. Now we need to deal with the right side. So Q enclosed. Let's do some work down here. So that means inside, remember, we've got my big sphere that has all the charge on it, Q, that comes out the radius big R. I'm just inside here. What fraction, like if I come halfway out, have I captured half of the charge? No, it turns out it'll be a fourth of it, but that's what we want to know. How much of Q, what fraction of Q lives in here? So the key to every one of these, always, Q enclosed will always be your density times your volume enclosed. And when I say volume, that means whatever dimensional version we have. That might be area enclosed, that might be a linear distance enclosed. And this density will always match up with this volume. Like in this case, I have a three-dimensional volume, so this will be coulombs per cubic meter, density per volume times volume, cubic meters. You'll have other problems later where our density will be coulombs per square meter. And by volume enclosed, I really mean area enclosed. So that will be in square meters. See, these will always cancel out to give you charge. So we got to find our density. Let's call that rho. And that's always going to be your total volume or area or whatever your shape is, the total thing mass per unit. So this is charge density. And I knew I was putting that upside down. I knew it as I was writing it. Density is always going to be total charge over total volume. Whatever your shape is, if it's an area, that would be total area. Okay, so my density here is Q, that's the total charge, divided by what's volume of the entire sphere, 4/3 pi r cubed. That's at every spot in this big sphere, the charge density is Q over 4 pi r cubed coulombs per cubic meter. That's how much charge there is per cubic meter. What's my volume enclosed? That's the volume that I actually care about with little r. His volume, this little guy, that's the enclosed, here's enclosed right here, is 4/3 little r cubed pi. Okay, so then my charge enclosed is always, every time, rho volume enclosed. That will be 4/3 pi Q over 4/3 pi little r cubed times the volume enclosed, 4/3 pi cubed. Okay, so the 4/3, the pi, that all cancels. I get Q times little r cubed over big R cubed. That's the fraction of charge that I've got in my little Gaussian surface, inside that surface. Okay, so now I put the two sides together. The flux through the surface, double integral of E dot ds must be the total charge enclosed over epsilon naught. This side, we went through all the work. That was magnitude of E, which was a constant, times 4 pi little r squared. That's supposed to equal q little r cubed over r cubed epsilon naught. Don't forget the epsilon naught. A couple of those guys cancel out. I can divide over the 4 pi and get, this is who I'm looking for. That's my goal. Equals q r over 4 pi capital R cubed epsilon naught. So that's in magnitude, and this points radially out. Okay, now let's do outside. That was only half of the problem. And I spent a whole lot of words and time explaining that. I'm going to go through this one much quicker. So here's my charge. Everything lives in here. My Gaussian surface now lives outside. So little r is now bigger than big R. I'm way out here away from the charge. Okay, so the left side's the same. This is still going to be magnitude of E. I'm talking about my Gaussian surface here. That comes all the way out, 4 pi little r squared. Nothing changed there. Now on the right, though, this is supposed to equal the charge enclosed over epsilon naught. How much charge lives inside here? Well, all of it does. The charge was right there. I've captured all of it. I got all of it. Charge enclosed is Q. Again, we're trying to solve for E. So divide over the 4 pi r squared, we get Q over 4 pi r squared epsilon naught. That's just Coulomb's law. This is literally where Coulomb's law comes from. Remember, we wrote Coulomb's law like this, but K is just 1 over 4 pi epsilon naught. K is just a shorthand for this stuff right here. So Coulomb's law literally is derived from Gauss's law. And this says if you're far away from a charge distribution, you can pretend it's just a point charge, a spherically symmetric charge distribution. You just pretend it's a point charge that's centered at the origin. Okay, let's do a plane of charge. Let me draw it like this. So this is an entire plane of charge. These sides, these go on forever. I've got some charge density, sigma. So this is sigma here is in coulombs per square meter, because this is a flat plane. There are no volumes here. I can't even talk about charge per unit volume. There is no volume. I can't even talk about total charge. My total charge is infinite. I've got an infinite plane. What I can talk about is, well, if I cut out a square meter of it, how much charge lives there? It's a charge density. I want to find the electric field, a distance r from the plane. Okay, well, first thing I need to do is just by symmetry. Imagine you've got the walls in front of you. Right now, you're looking at a wall. Let me close some stuff because my battery is starting to get low. I don't know if you guys can see my battery. I think you can only see, I don't know if you can, but the little red there says I'm going to die soon. So imagine the wall right in front of you. The electric field has to point directly out from it. It has to. Otherwise, the universe wouldn't make any sense. If I've got an infinite sheet and the electric field points at some weird angle, rotating this sheet shouldn't change anything. If I rotate like around like this, the electric field has to point away. So first, by symmetry, E must be perpendicular to the sheet. Similarly, if I'm out some distance r away from the sheet, it wouldn't make any sense for E to be bigger here than it is here. The universe doesn't know the difference between these spots if they're both the same distance away. So at a distance r, E is constant. That's going to happen on every one of these. Otherwise, we can't use Gauss's law. Okay, so we need to decide on a Gaussian surface. I'm going to redraw my picture here. And just for fun, maybe I'll do this one two different ways. I'll do it with a cylinder and with what we call a Gaussian pillbox. So I'm going to do it with the cylinder here. Let me draw that one dotted. Again, my drawing skills are not great, so you're going to have to use your imagination here. But I've got this cylinder, I've got this plane, and this cylinder is sticking out in front of the plane, and then this dotted part is behind the plane. So if I were to kind of look at a cross section, the cylinder is coming out at your eyeball, and then the other half is behind the screen. And I'm coming out some distance r. And then we have to decide, if you're making up your Gaussian surface on your picture, you have to show all the parameters here, all the dimensions. Let's say this guy has a radius of a. I didn't draw my picture big enough to really label it. I put a little tiny a on there. So let me draw it in this picture, a little a. That's the radius of my cylinder. I made that up. Now, with these Gaussian surfaces, anything you make up is going to cancel out. Okay, so the double integral of E dot ds, the flux through this surface. Okay, so we've said E must be pointing perpendicularly away. So through this circle right there. So we've got this circle, we've got E pointing perpendicularly through it. That's this circle right here. Similarly, on the back side, back here, I had that dotted circle. E is pointing this way. E pointed away from the sheet. What about on the sides? Imagine a soup can. So I'm going to draw a vertical can here. What about if you take the label off the soup can? What's the flux through those sides, or that cylinder itself? Well, E is pointing this way. The normal vector points away from the soup can. So on these sides here, perpendicular vectors have a dot product of 0. The flux through the label of the can. Now I'll draw it like this. The flux flowing out this way is 0. All my flux is flowing through the ends of the can. And I have to say that. This is important. You have to write that down. The flux on the label is 0. I'm going to have flux here. Let's call this flux 1 maybe. and then flux back here flowing out the back end. Let's call that flux 2, and then this guy here was 0. So flux 1 would just be E times A. What's my area? It's a circle. Same thing on back here, on this back end. I'm going to call that one 2. So the double integral of E dot ds will be 2 magnitude of E pi r squared. Or another way to think of it, pull the E out, double integral of dA would just be the area that actually has flux, not the entire surface area of the whole cylinder, only these 2 areas, because the flux coming through this part was 0. Okay, what about the other side, the Q enclosed? Q enclosed is always going to be your density times the appropriate kind of volume enclosed. Here, my density was coulombs per square meter. So by volume enclosed, I mean area enclosed. We don't have any volumes. That's coulombs per square meter. I multiply by square meters, I get coulombs. Okay, so my picture here, how much of my total infinite amount of charge did I capture in this picture? This amount right there. All the charge lives right there in that little circle. So this is going to be sigma. That's going to be part of my answer. Sigma is in my answer times pi r squared. So we put these 2 things together. Double integral of E dot dA or ds, those mean the same thing, will be Q enclosed over epsilon naught. So 2 E pi r squared is sigma pi r squared over epsilon naught. The pi r squared cancels out. We get magnitude of E equals sigma over 2 epsilon naught. Okay. We're going to talk next time about conductors and parallel plate conductors, parallel plate capacitors. It's made using an infinite sheet just like this. I can do some really cool problems there. All right. Well, this is really going to go long, but I'm going to cover everything we could possibly cover here. Let's do this same problem with a pillbox. Okay, so I still have sigma. Now my Gaussian surface, I don't like doing pillboxes because I don't draw this very well. I'm trying to draw a rectangular solid. Well, that is a terrible drawing. So let's look at it like a front view. So I have to make up some parameters here. I know I'm coming out a distance R. So this distance that this thing sticks out in front of the plane is R. And let's say this is a square. I don't know, maybe both of these are L. So this front piece is sticking out a distance R in front of this sheet. And again on the back side. So it's a rectangle sticking out of this plane. Okay, now we know our electric field points perpendicularly out. So like right here, E is coming straight out at our face. So I've got 6 different fluxes I have to find. I've got the flux right here on this front piece, all 4 of these sides, and then this back piece. By the same argument we made before, E is pointing away from the surface. So on this side over here, this entire side, E is pointing like this. My normal vector is pointing directly out at my eyeballs. Those are perpendicular. The flux is 0 through all 4 of these sides around here. The only flux we have is through the front and back. So flux 1, E dot ds would be since we know it's constant, E's constant on that surface because we're a distance r away. E times the area. That's just area. Area of a square is L squared. And we have 2 of those, one on the front and one on the back. So our total flux, double integral, let's call that number 1 there, of the entire thing will be 2 magnitude of E L squared. All right, what about charge enclosed? So I had my pill, oh my God, I'm gonna have to try to draw this again. So the intersection of my Gaussian surface and the sheet is this square right here. So my charge enclosed will be sigma times the area of that square right there, the area enclosed. So that'd be sigma times L squared. So putting the 2 sides together, charge enclosed over epsilon naught. The L squareds cancel, they better, because I made up L, it better not appear in the answer. And we get magnitude E is sigma over 2 epsilon naught. So using the Gaussian pillbox is less math, but it's much harder for me to draw the picture. So I always do the cylinder, but we get the same answer. Okay, what if we have, I think this is your group assignment, an infinite cylinder. Of radius r. I'm not going to go through it again, but I did a video for a line of charge. This is the more advanced version, the infinite cylinder. We want to find E inside, so little r less than big R, and E outside, r greater than big R. So we're going to pick, our charge density. We need a volume charge density here, rho in coulombs per cubic meter. Okay, so we pick a Gaussian surface. So I'm going to choose a cylinder. You want your Gaussian surface to have the same kind of symmetry that your charge distribution has. Cylinder of radius little r and length L. Now, I'm going to have little r's in my answers. I better not have any L's in my answers. That's something I made up. I am now creating this arbitrary Gaussian surface of length L. The answer shouldn't depend on how long I choose to make this. It will depend on how far I am away from the center. That's a poor drawing. Okay, so here's the entire thing. So I've got this little cylinder that lives inside this infinite cylinder. Okay, by symmetry, the electric field has to point radially out from the center. So E must radially out. It wouldn't make any sense for E to point up at some angle. E must point out. So let's draw a couple E vectors. Maybe over here, E points out. So along that surface, E is always going to be perpendicular to the surface. Also, these are things you got to note. E must, it has to be constant at radius r. It wouldn't make any sense for E to be a little stronger at this spot than it is at this spot. This thing's infinitely long. How can E be changing as I just move up and down? It wouldn't make any sense. Okay, so we've got three different surfaces to consider. The label of the soup can, the top, let's call this flux 1 up here at the top. Flux 2, the flux that's flowing out through the label of the soup can, and flux 3, whatever flows out through the bottom. So on top, E points out like this. My normal vector points straight up, perpendicular to the surface. E is parallel to the surface. E is perpendicular to the normal vector, so the flux is 0. E just rides along the surface. Flux measures how much you pass through a surface. Here, E is riding on top of the surface. Same on 2. Down here, there's no flux flowing out. All the flux is flowing through the label of the soup can. So this will be and we're talking about the label of the soup can here. Now we just said that these two are perpendicular there. So the dot product of perpendicular vectors is the product of the magnitudes. I can replace that dot product and get rid of all these little vector symbols. Just put a magnitude. We also said E must be constant along that surface. So I can pull that out. Now I just need surface area. Not the surface area of the entire cylinder, mind you, just the surface area of the label of the soup can. So imagine taking this label right here, all of this stuff, and rolling that out into a rectangle. This was L, so this side would be L. This length of the soup can label would be the circumference of the circle, 2 pi r. So that area would be 2 pi r L. I called it little l. That's the flux through the surface. What about, sorry, real quick, I have to get my charger. I'm about to die. I'm going to pause this recording. Okay, and then I forgot, I went through the rest of the problem and forgot to turn the recording back on. So I really don't even remember where I left off. I think we were in here. So we had inside here, and we had an electric field that goes up like R. So our volume enclosed was the volume inside here. That was pi r squared L. It's volume of a cylinder times rho. Now when we're outside, we've got the same kind of situation. I've drawn my Gaussian surface. You have to draw the picture. That's part of a solution, is drawing this picture. My Gaussian surface is a cylinder with radius little r bigger than capital R. So my charge only comes out to here. My surface goes all the way to here. So just like we did before, the flux through the top and the bottom of my surface would be 0 because E is running along those surfaces, and all the flux will come directly out the soup can label. So that flux, notice I put flux equals 0 on top and bottom. That flux will be same reason it was before, magnitude of E times the area of that soup can label. Here's where things are going to be different outside. The charge enclosed will be rho times the volume that actually has charge in it. My charge does not come all the way out to the edge. The charge stops here. So volume enclosed is not the volume with all that empty space, it's the volume where the charge is. And that only comes out to capital R squared. So the volume of this cylinder here, not the infinite cylinder of radius or of length L. So now put all that together. The L's cancel, they better. My answer will have an R in it because the electric field depends on distance. It won't have an L in it. The pi's cancel, we get E equals rho capital R over 2R epsilon naught. And now if we put all this together, the electric field from the center goes up like little r. It's increasing as we get further and further out. But then once I get outside, it starts dropping off like 1 over r. Capital R is a parameter in the problem. Little r is my variable. So until I reach the boundary, the electric field's getting bigger and then it starts dropping off. Just like a line of charge. The electric field from a single line of charge looks just like this. It goes like 1 over r. So far away, a cylinder of charge looks like a line. Okay, now I can stop recording again.